Hello everyone. Hello everyone. Today inshallah I will talk in specific about the intersection, the union, the addition. This part is usually hunted in plenty of statements, especially you know the nature of things. Of course, the second midterm will be exactly like the first. It will be 10 questions, each one of them was five statements, and he will ask you for the correct statement in each one of them. I will try to share one of the second midterms as soon as possible, but Ziad will just refresh my memory, okay? Because I usually forget, okay? And I will share it with you. Today, inshallah, as I told you, Chef Harakari, we will talk about the intersection, union, and the sum of subspaces. There is a huge difference between it needs a good understanding of the intersection and the union and the various spaces. In the first paragraph in linear algebra, the concept of intersection, union, set addition is usually related to operations performed on sets and vectors. We are dealing with sets mainly. So sets or matrices, and they are similar to each other. So the concept is really related to these to these types of objects. So once we say A intersection B, A is supposed to be a subvector space, B a subvector space from a certain vector space. It represents all the elements shared between both of them. So it is actually the vectors that exist in both two subvector spaces. Intersection meaning in subvector spaces, denoted by the intersection symbol, it is the set of elements or vectors are both in A and B simultaneously. Result, the intersection is a set of vectors that are shared by both of them. Since it is a set of vectors that's shared by both subvector spaces, so it is by itself a subvector space. So first of all, I have A and B. They are subvector spaces. So they have addition closure, they have multiplication by scalar closure, and they have the origin. So once you are seeking the shared elements, you will have the origin at least. Am I right? And also some of the elements, so the result will be a subvector space. The intersection, as I told you, it's already stated in here. So the intersection always produces a subset of both A and B. R vector space or something, then the intersection is also will be the same. The intersection can be empty, which is just containing the not set, or if there is no common elements between both sets, but between subvector spaces, it will have at least the zero vector. And we will know down the road that's gonna develop also a certain type of addition. We will see it, inshallah, by the end of this lecture. So, for a set, for example, 1 and 0, 2 and 0, and for beta, 1 and 0, 3 and 0, for these two spans, the intersection is gonna be 1 and 0. It is the set of all elements on the shape of 1 and 0. Okay, now for the addition of subvector spaces, and this is important because there is a difference between addition and union. In addition, the structure of the subvector space will change. We will see this together. Okay, in addition, the set addition in the context of linear algebra usually refers to addition of two sets of vectors, of vector space or subvectors, not the individual vectors. So it's not the vectors by themselves that you are adding to, because if you are adding this set to that set, it's going to be union. But in the addition of subvector spaces, the structure by itself, it will change, as you will see. For example, if I have A plus B, this is subvector space and that's a subvector space, and you're getting the addition of both of them, the forming elements in both of them will be added together, where A belongs to A and the B belongs to B. Okay, the result of set addition is a new set, not a single vector. It's going to be a new set. For example, Ms. Nada, Fatim. For example, and this is really a very important example, Fatim. مش معايا. اوكي بص الفرق بين الاديشن واليونيون. In addition, I have the set with the span 1 and 0. This is another set with a span 0 and 1. Once you do the addition, you will add the elements which are represented by 1 and 1. Okay, so actually the structure of the elements it changed. So I'm talking about set A, which is the set of 1 and 0 are the elements on the x-axis. I'm talking about the set of 0 and 1, which are the elements on the y-axis. Once you add them together, you do the addition, you will have a new element added to those ones. So actually the set will be bigger, will be bigger than both of them together. Not just only the x-axis and y-axis, but it will contain the elements with 1 and 1. So the structure by itself changes in the addition. That's the addition of subvectors. As I told you, this is subvector A, this is subvector B. Once you add them together, you will get a bigger subvector space. And of course, it's a subvector space because it contains the addition, closure, the multiplication by scalar, and everything. So, however, if we are dealing with entire subspaces like R2, the sum of two subspaces may be, in some cases, bigger than the original subvector spaces, okay? Or the union of them. طيب, if I am doing a union, what's the difference between the union before even we define it? The union and the addition. Bijana, the addition here we added the elements of A and B. And we have a new element. The union, it means all the elements on 1 and 0 and or the elements with 0 and 1. You will never find an element 1 and 1, okay, in the union, because union means I will take the set from the elements from this set and the element from that set and put them all together, okay? But I'm not going to combine the structure or change the structure of these sets, okay? This is mentioned. Okay, union meaning the vector subspaces. Definition: the union of two sets, as I told you, it is the set of elements that are in either set A or set B or both. It doesn't involve, it doesn't involve any addition of elements, but rather it simplifies, combine the elements of both sets both together. So it's just adding the elements, but it's not implementing new elements due to this addition process. The union is a set containing all unique elements from both sets without duplication. This is why, in general, once you try to get an union in probability or something, you have the probability of A plus probability of B minus the probability of their intersection to avoid the duplication of elements. Okay. In the context of vector sets, it would include every vector in either, but wouldn't involve any operations like adding together or something. The union operation doesn't change the dimensionality, doesn't change the dimension of your vector space. It's not like the union, it may change it. The union of the addition, it may change it. The union of two subspaces is not necessarily a subspace by itself. Unlike the sum of spaces, the union may not be closed under vector addition. And this is very, very clear from an example I will show it to you. So the reason that the union may not develop a subvector space also, although these two subvector spaces they are subvector spaces, but once you add them together, you may be ended with a not subvector space, missing the conditions or something like this. I believe I have an example here, which is going to be really, very nice. For 1, 0, 0, and 1, as I told you, if you have the addition, you have the set of all elements on this image, 1 and 0, or the x-axis, and the image on this 0, which is 0 and 1, the elements of the y-axis, but you will never have the element 1 and 1, okay? Which is different than the addition. So, intersection focused on the common elements, union combine all elements, both sets, without any addition of vectors. Set addition involves adding various elements to each other. Also, I've joined this comparison between the intersection, union, and set addition to be with you. I believe I sent you this PDF earlier, and then once I finish, I will send it to you also on the WhatsApp. So it contains the details of definition, result, operation, resulting sets, covering summary for all the previous information. If F and G are subspaces of vector space E, and F intersection G is a subspace of E also, that's the statement that I've repeated more than once. Let's do this problem. If you look to this problem, you will find F represents a subvector space from R4 and it contains, of course, since it's in R4, so you will have 4 components, A, B, C, and D, with the following remarks. That's A is equal to B, so it's written A minus B, and A minus B minus D is equal to 0. Remark that A minus B minus D is equal to 0, it's exactly like saying D is equal to 0. Okay? معايا يا جنى؟ Why? Because A minus B is equal to 0. So if you just remove A minus B and put 0, you will have negative D is equal to 0. So now I can reduce the shape. For the second set or the second subvector space, you have B is equal to C and also D is equal to 0. You want you to find F intersection G, which means I need to find the set with all of these conditions happening. So I have to satisfy all the conditions. That means the intersection. The conditions of the first with the conditions of the second. So actually I'm searching for the intersection will be represented by the elements in R4, A, B, C, D, but with A minus B equal to 0, A minus B minus D equal to 0, and B minus C is equal to 0, and D minus D is equal to 0. If we try to go through them, I believe from here, from this relation, I will have B is equal to C. So, remark step by step. I will have first B is equal to C. And also I have D is equal to 0. So this is number 1, that's number 2. And I believe from this guy, I have A is equal to B. So I can say A is equal to C, B is equal to C, C will remain the same, and the D is gonna equal to 0. So the elements of the intersection, F intersection G, will be the set of elements with these conditions. I will replace A with C, B with C, C element, and the D is equal to 0. And that's for C belongs to R, which can be spanned. The span of this set is gonna be 1, 1, 1, and 0. That's gonna be the span of the intersection. Okay? All the conditions are satisfied for this intersection between these two groups. Okay? So once more, as I told you, I'll start to hold them all. Just to give them a good look, try to guess the relation, or try to find the relation, simplify it. Try to find to satisfy all the conditions. It will be satisfied this way. So I have now A is equal to C, B is equal to C, and D is equal to 0, which will result into all of this. I can take C as a common, which will leave me with the span of this group to be 1, 1, 1, and 0 for the intersection. I will give you more examples through this lecture, inshallah. Procedure to obtain intersection of two subvector spaces. First of all, obtain the system of S1 of linear equation with solution set equal to F. Same way if you are working with S2, because you will have first set and second set. This is how to get the intersection. So I will obtain the system from S1 of linear equation with a solution set, okay, equal to F. Consider the system S made up of all equations of S1 and all the equations of S2, that's the intersection satisfying those conditions. The solution set of the system S is F intersection G. This is actually what we do. We put the conditions all together, or satisfy each equation first, then equating them or finding the combined between them. Unlike the intersection or subspaces, the union of subspace doesn't have to be a subspace, and we already did go through all of this. This is also the same example or another example on the elements on the x-axis, the elements on the y-axis, and he won't show you the union of these two elements. The union of these two elements is going to be only the elements on the x-axis or the elements on the y-axis, both of them separate. Okay, and this conditions, Farid, is not gonna cover the case of the rest of R2, so it's not gonna be closed under addition. Okay, once more, the given sets in here, the first set is gonna cover x and 0, which is the x-axis. The second set is covering all the elements on the y-axis. So getting the union of both of them, it means all the elements in here, and the origin is not going to be repeated with all the elements on the y-axis. But missing all of this parts, this is not going to be involved in our new set. Do you read me? ماشي يا شباب؟ طبعا same way like 2 and 0 it belongs to the union. 0 and 3 belongs to the union. This is point on the y-axis, that's going to x-axis. But for the point 2 and 3 doesn't belong to their union. Okay, if and G be subspaces of vector subspace, then the union is subspace if and only if. Okay, this statement is to, in particular, answer the question if union G, if is a subvector space and G is a subvector space, the result in all times is not gonna be a subvector space. No, in general, there is a necessity to have a subvector space at the previous examples. But sometimes you will have a subvector space. Like, when are you going to have a subvector space in union? It will happen, but under one condition. That's F is a subset from G, or vice versa. G is a subset from F. So once you get the union, you will have a subvector space. Okay? So that's the exception from the general statement of the union issue. Of course, if the addition, you know the addition, we already went through it. The sum of two subspaces of E is a subspace of E. Is representing the addition, I believe. This is also the y-axis, the x-axis. Of course, once we add them together, we will have the element of x and y, which covers all R2, which is gonna be a subvector space. So any element in R2 is gonna consist of x and y, and easily can be found by the addition process. That's a proof it's gonna be a subvector space. So sum of two vectors is subvector space. In generally, if I have, let E be a vector space and F and G are subvector spaces of E such that F contain, this is the vectors that generate this subvector space, and the V1 up to Vs are the vectors that are generating G. So adding them together, it means you will add the vectors generating F plus the vectors generating G. That's what happened previously. If you have the first set with the span of 1 and 0, the second set with the span 0 and 1, once you add them together, you will have the new span, which is 1 and 1, covering all of them. So you simply can add 0, 1, 1 and 0, and it will be added together for the combination of the addition process. Here's also another problem, and he wants you to find F plus G, okay? F is giving you with the condition, and G is giving the generating set by itself. Of course, it's really very simple to get the generating set for F if you make the replacement. So I can, first of all, get the span of F or the basis of this set by simply doing the condition. So F as a subvector space, I can replace X by Y plus 2Z, and I have the Y coordinate and the Z coordinate such that Y and Z belongs to R. So simply I can separate them first, okay, plus that's the second one, such that Y and Z belongs to R. So the first one is gonna be Y for the first coordinate, Y for the second, and 0 for the third coordinate. The second is gonna be 2 over Z, and then 0 plus Z. So you will have 1, 1 and 0, okay, on the set, and 2, 0 and 1 for the other set, forming the plan or the subvector space of F. I made the, first of all, the substitution. Then I've isolated both of them, taking the constants by the previous, as we did previously. So the first step, as I told you, make the substitution. Here we go, that's the two vectors. And so this is F with the bunch of vectors that generate F. If I want to get the addition of f plus g, all I have to do is to add those vectors to those vectors, okay? And that's gonna be the new span for the f plus g. Of course, if I want to check the basis of this set, I can put them in a matrix, taking each column as each vector as a column and do the row operation in order to reduce them to get to a basis. Do you remember the previous lecture? Mr. فريد انت معايا ولا باصص في السقف مش جايب النضاره عامله ريفلكشن؟
انا باصص في الاجابه مش فاهم الست اللي هو يعني احنا تمام جبنا 1 1 0 2 0 1 بس انا مش عارف الاثنين التانيين دول جم ازاي.
مش انت بتعمل اديشن للاف جي؟ فبتحط الجنريتنج ست دي مع الجنريتنج ست دي. فكل اللي حصل دول انا مديهم لك عادي اهم شايفهم؟ ايوه. ودول انا مديهم لك انت جبتهم. تمام. حطيتهم على بعض، ده معنى الاديشن. تمام. طيب انا بقى مش متاكد او عايز اتشيك ايه الفرق بين الاسبان والبيزس؟ انت حضرت امبارح تاني؟ لا كنت بذاكر كيمستري. صح. طيب في فرق between there is a difference between a span and basis. Span it's generating set of vectors to generate a subvector space, but the basis is the optimal number that will generate this space. Okay? طيب how to be sure that this set is the optimal one? Just put them in a matrix. Okay? Representing each vector of those as a column. So you will have 1 1 and 0. 2 0 and 1. 1 0 and the negative 1. Then 0 3 and 1. And then try to reach a reduced echelon form in order to get a reduction for the rank. Okay? If it stayed the same, so these bunch of vectors are linearly independent. And once they are linearly independent, so the span is going to be the basis. But if there is one of them is linearly independent, I can remove it from the span to decrease the number of vectors in the basis. Are you with me? Say that. Also, you didn't appear yesterday. Yes? Okay. Who attended yesterday? Ziad, Fatin, Nada. Did you study or did you remember anything from yesterday?
Yes.
We talk about the span and how to reduce it to reach basis. Okay. معايا فريد؟ معايا. Okay. Let E be a vector space. Okay. خلي بالك من الديفينيشنز دي they will be equal to each other or equivalent. وده مهم في الجزء بتاع الستيتمنتس. Once he asks you about the correct statements or which one of them. Also, I want you to take a good care of sometimes he give you statements of two parts. One of them is correct and the rest is not correct. Do you read me? Yes. So the statement by itself, it contains a part of a correct answer. But of course, in general, the statement is going to be wrong. Okay, you're not going to choose. So this is very, very important to understand. Let E be a vector space and the F and G are subspaces of E. The following statements are equivalent to each other. Number one, if U1 to Un is a basis for F, so it's a subvector space, the basis of subvector space. And V1 to Vs are another set or the set of the other subvector space of G. Combining them together is a basis of F plus G. This is what happened in the previous example. Okay, the F intersection G is equal to the 0 set, which means they are linearly independent set. This is linearly independent set, and I can't generate any one of them from each other. So the V's are not going to be able to generate from the U's and the vice versa. How to be sure, Farid, that the V vectors can be generated from the U's or not? If they are linear combination. Okay, so once more, let's get back to this point. I have here two sets for two subvector spaces. A subvector space G with the vectors 1, 0, negative 1, 0, 3, and 1. And the other subvector space which is double 1, 0, 2, 0, and 1. Okay? So the sum of these, first of all, the intersection between these two subvector spaces is gonna be the origin. This is number one. Which means also that those vectors cannot be generated from those ones. So I can't generate 1, 0, negative 1 from the combination of these two vectors. Okay, do you understand what I'm saying? And I can't generate that vector also from this set. And the same way, like vice versa. So I can generate any of them from each other. So the subvector space of their addition will be those vectors from U or from the first subset plus the vectors from the second subset. You understand what I'm saying? Okay, once more. So if U1 up to Un is a basis of F and the V1 up to Vs as a basis of G, getting their addition, it means this subvector space plus or the generators or the basis of this set and the basis of that set combined together. It's exactly like saying that their intersection is equal to 0. They are the same thing. If U and U dash belongs to F and the V and V dash belongs to G are such that U plus V is equal to U dash plus V dash, then U is equal to U dash and the V is equal to V dash. That's condition for the equating of vectors in both subvector spaces. Okay, here we are going to talk about the direct sum. The direct sum of vector spaces. Let F and G are subvector spaces of a vector space E. We say that E is a direct sum of the subvector space F and G, and they denote it by this symbol. This is the symbolization of the direct sum. The direct sum will happen exactly like the previous example. I've taken the basis of the first plus the basis of the second, and I will add them both together. And this will happen only when their intersection is equal to the origin. Okay? Also, it means that the set of bases for the first subvector space is not going to be generated from the second, and the vice versa. So this is really, very important. If for all W belongs to E, there is a unique pair U and V can be formed from both of them, where U belongs to F and V belongs to G, such that any vector out of this vector's direct sum is equal to U plus V. In this case, we say that F is a supplemental subspace of G. تاني عنصر خلي بالك ان الانجليزي هنا متلخبط مع البرتغالي شويه، فاهم؟ في الترجمه يعني. فهنا بيقول in this case we say that F is supplemental subspace of G. اوكي؟ او العكس، اقدر اقول انه G is a supplemental subspace of F. ده معنى ان هو بيكتب الرمز وبعدين يفتح قوس ويحط الرمز التاني. معناه انك ممكن تقراها you can read it in two ways. Either an F and G supplement to each other, or G and F supplement to each other. Okay. In these statements, I like you to take a good care about these expressions, because if he put supplemental subspace, this is the meaning of supplemental subspace. It's related to the direct sum. Okay. We also say that vector U is the projection of W onto F. Of course, I can say V is the projection of W onto G. Since U is a vector belongs to, if U belongs to F and V belongs to G. So that's the meaning of the projections. We will speak a lot about the projection of a vector into a subvector space and its components down the road. But this is just the first one. So I'm going to repeat it once more. We also say that the vector U, which is a part of W, ما W ده بيكون من U and V, okay? لأن أنت هنا بتعمل direct sum فكل element in W is going to be a direct sum from the vectors that belongs to both F and G. So we can say that the vector U is the projection of vector W, okay, and into F according to G, and that V is the projection of W into G according to F. Okay, that's the meaning of this projection. We will go through it, I believe, in the next lecture. Direct sum of subspaces definitions. That's definition specific. every vector in V can be uniquely written as the sum of vectors in A and vector B. That's the symbolization of the direct sum. For every V belongs to V, there exists a unique vectors. A belongs to subvector A and B belongs to subvector B, such that V can be combined from A plus B. The intersection of A and B is only the zero vector. So there is no other vectors combined between these two subvector spaces. Also, this condition shows that the composition of any vector in V into a sum of vectors from A and B and is unique. If A and B contain any non-zero vector, then the sum is not going to be unique. Then a vector could be written in two or more ways, and so it's not going to be unique. So the condition for having a direct sum, that the intersection between these two subvector spaces is equal to 0. And the formation of any vector in the direct sum subvector space is composed of a unique formation from two vectors in both subvector spaces separately. Consider a vector space in R3. Let A and B be the following subspaces. This is A. السبان بتاع ال A هو الset of elements 1 double 0، يعني الاليمنتس اللي موجود على الاكس اكسس بس في 3 dimension. بعدين B السبان بتاع 0 1 and 0 which are the elements in Y axis in R3. Okay. In these two cases لو انت بصيت على first set والsecond set الانترسكشن واحد على الاكس اكسس points in X axis والتاني points بتاعت الواي اكسس. الانترسكشن بتاعهم is gonna be just only the origin. So if we got it's every vector in V can be uniquely written. So the subvector space which is represented by their direct sum as the sum of vector from A and the vector from B, and the intersection of both of them is equal to 0. So now I can add x double 0 plus 0y and 0 together. So the combination that I will have contains both elements. So where x belongs to A and y belongs to B. This decomposition is unique, and the intersection is only 0. So it's a direct sum for these two vectors. Either R3 can be considered or can be composed of A direct sum to the elements of B. Of course, this set of elements, once you add the A and the B together, you will have X, Y, and the 0, which represent the set of elements in a plane, not with the Z axis, which is a subvector space from R3. Already contain the origin and contain the set of elements that's in the plane of by 1, which doesn't have a Z value, but have X values and Y values. Okay?
بس كده
Okay. Intersection union.
حسيت الستك خلاص يعني
لا مش قادر. اوكي بس عايز اخلص الجزء ده قبل ما انقل على عايز بس على الستيج بعدين عايز ادي شويه مسائل. I wanna give you some problems علشان اخلي الفكره دي تبقى اوضح بالنسبه ليك. انا قاعد عمال اتكلم ان دماغك معايا.
ايوه
فبقول المثال اللي فات اكن خلاص انت حافظ المثال اللي فات.
لا ده كده
اوكي ماشي. Let f and g be subspaces of vector subspace. The following statements are equivalent. الدايركت sum ده معناه ان الانترسكشن بيساوي 0 ومعناه ان كل فيكتور ان E هو عباره عن بيتكون من vectors already exist in f and g both together. So these two statements are equivalent to each other. Okay, تعالوا نبص على ده. يقول example R3 consider the subspace of f. It's the set of elements x, y, and z belongs to R3 but with the condition that y is equal to 0. معايا؟ لو انا حطيت y equal to 0 يا فاتن مش معايا خالص النهارده. لو حطيت y equal to 0 يبقى انا بتكلم على الست of vectors اللي هي فيها x 0 and z اللي هم مين البيز بتاعها لو تعرفي تطلعيه البيز بتاعها سهل 1 double 0 1 double 0 0 0 and 1 دول التو فيكتورز اللي لو انا جمعتهم على بعض هيديك 1 0 and 1. Am I right? Okay. And for G it is the set of vectors. خلي بالك set of vectors اللي فيها الاكس بيساوي كام؟ 0 والواي بيساوي الزد يعني the set of vectors 0 1 1 0 1 1. اوكي؟ تاني انا I will change x by 0 والواي ب z so it's gonna be 0 1 1. That's the set. هنا it's gonna be x 0 z صح؟ So it's gonna be 1 0 0 0 0 1. You add them together. This is how to see the x component and the z component, okay? And the h is representing another subvector space, belongs to R3, but under the condition that y is negative z. So actually the basis is 1 0 0 and the 0 negative 1 and 1. Are you with me? اوكي فاهميني يا شباب؟ انا طبعا شغال ان انا بعمل السبستيتيوشن وباخد الاليمنتس دي از common. ماشي؟ اوكي very good. Prove that in R cube is a subset of F plus G, and prove that also in F plus H is a subset of R3. I will stop here. I will continue next lecture, inshallah, from this part, and I will cover this problem. I need you to understand it very well. So, first of all, study the rest of or the lecture of today, and I will continue this part tomorrow, inshallah, next lecture. All of this is related to the previous problem, and then I will finish, go to the dimension theory and how to use the matrices, okay, in solving vector spaces. This is going to be the last part in this lecture. Hopefully, I will finish this chapter within the next lecture or the lecture on next Sunday, inshallah. Okay, thank you.